This is sections 8.3, part 2, the trigonometric integral. Now let's look at the example 5 and 6, where we have, see these two problems, we have tangent and secant, which is good. Remember, tangent and secant go together, sine and cosine together, okay? So when these happens, tangent and secant together, that means we will be trying to use the substitutions, okay? So the first one here, let u be, again, pick one in tangent and secant. I'll pick tangent. Okay, derivative view, a tangent, is secant square. And you see that why it works initially is it is secant square, and we do have secant square. In fact, we have secant to the fourth. And so what you're going to do, you're going to rewrite this integral as tangent to the 6. Instead of secant to the fourth, you split into secant square times secant square. All right? So that ensures we have secant square x dx that become a du in the next step. But the problem is, again, since you turn into tangents, everything needs to be written in terms of tangent. And you see that there's a secant square there that we need to handle. So somehow we need to change this to tangent. Okay, change to tangents. So to do that, you have to use identities that involve tangent and secant. So the one that we're using is tangent square of theta plus 1 equal secant square theta. Right, so here's identities that we're going to use. Okay, so here I'm able to turn the secant square of x into tangent square of x plus 1. So let's see how that works. So that means good. You have tangent to the 6. And then that is times secant square of x dx. You see everything in terms of tangent except that one, secant square, say secant square dx, that turned into the u. The tangent is the u, right? So now we have this new integral with our trig function, that's u to the 6th power, and then the time, the tangent is u square plus 1. So see how that go. Now it's gone, right? The trig function is gone. I can integrate. Still, I have a bit problem. There's multiplications there. Well, that's not the problem. All you do is multiply it out. U to the 6 times u squared is u to the 8 plus u to the 6 du. And once you have that, I can integrate from there, right? So that u to the 9 over 9 plus u to the 7 over 7. And this is integration step. That u to the 9 over 9 plus u to the 7 over 7 plus constant. And the last step is just the substitution back. Right, substitution back. So u is what? Tangent. So we have tangent to the 9 over 9 plus tangent to the 7 over 7 plus constant. Okay. and that is the answer for number 5. If you look at the number 6, well, it's still tangent and secant, right? So at first, we feel like we can still do the same with the substitution use tangent, but you're going to soon realize that that doesn't work quite well, because although I can, when I take a derivative, right, I still have secant square and then you have secant cube. Then what happens is when you rewrite that to have secant square, we actually split that into secant x times secant square x, where that would turn into du as before. That's a tangent, and since u is tangent, you need to express the secant in terms of tangent. You see there's a problem there. If it were secant square, that's equal tangent square plus 1, but it just have secant theta there. Now you might argue you can get secant by itself by taking root on both sides. So technically yes, but when you do so, that becomes a square root, tangent square plus 1 there, so it becomes like u square plus 1. And then let's use it a third. You can change the variable, but end up with the integral kind of hard. It's impossible to integrate even without the trig functions. So this is just our choice. It's not a wise choice at the beginning. So what we're gonna do instead is of letting u be tangent, okay, we can switch our choice. Switch a choice. Instead of tangent, now the other choice you have is secant. Right, so that you be secant of x. Then the derivative of secant is secant times tangent. Secant x times tangent x. Now keep that in mind. This time du is secant x tangent x. So you do need secant x tangent x in the integrand, which actually I do. I have 3 of those. 3 of those, okay? So what you're gonna do is to rewrite that as, instead of tangent q, that's tangent squared times tangent, right? Tangent greater than tangent. Time, instead of secant q, it's secant square x times secant x. Right? So I split, save the secant and save the tangent x there. Again, trying to match this with this. It'll be our du here. Now the variable is u, which is secant x this time. So you want to change your tangent in terms of secant square. So you can see up here, I have that relationship, right? If you want to write tangent in terms of secant, well, I saw, or subtract 1 on both sides, then tangent square of theta is secant square theta minus 1. Right? Tangent square, secant square minus 1. So this is tangent square minus 1. And now look how I change. That's integral. That is tangent square times tangent square minus 1 times secant x times tangent x times dx. That will be a du. Then u and u, I have u here, I have u there. and that become integral u square and time u square minus 1. Okay, well then what's next? We don't have more, we have integral integral trig functions. So we can multiply it out here so that we use the fourth minus u squared du. And from here, no more trig and no multiplications. I can now integrate that u to the fifth over 5 minus u to the third over 3 plus constant. And of course, we can go back to original functions, where u in this case is secant. So the final answer is secant to the fifth x over 5 minus secant of x to the third minus secant over 3 plus c. Okay. Now that leads to the following. If you're trying to see the strategy, what happened is it says when power of secant is even, this is what you do. Power of tangent is odd, this is what you do. Again, I don't suggest you do that way. Just choose one for you, and if it doesn't work, you switch. Okay. Now we look at numbers 7 and 8. 7, you have sine times cosine. Okay. Perhaps I do a strategy here. Okay, I'm going to run number 7. Here. We have the integral of sine of 3x and cosine of 5x, 3x and 5x, or 5x and 3x. So that is 5x, and that is 3x. Now we see the problem in this one is a multiplications, right? So for multiplications, sine and cosine, we will be using this identities again, sine and cosine, half sine plus sine, half sine plus half sine plus sine. So this integral now could be written as half of sine plus sine. Okay, so that's how I remember. And what's inside is the subtraction, 5 minus 3x. Okay, so that will be 2x, right? Side of 5x, you have 5x minus 3x, and then you have 5x plus 3x, so that would be 8x. Now you can see it's become sine plus sine, and we don't have problem integrating this. It's a half, and derivative sine of 2x is negative cosine of 2x. Right, derivative cosine of negative sine. And then again by chain rule, we have 1/2 there, and minus that's 1/8 cosine of 8x. Sorry, we integrate that, so it's gone, and we have this Just finally rewrite it and just clean it up. Just clean it up a little bit. It is 1/2. Well, maybe I should multiply it out. We have a plus constant. So negative 1/2 to negative 1/2. That's negative 1/4. Cosine of 2x minus 1/16 cosine of 8x plus c. Okay, so that's the answer. If you look at the last problem here, number 8, and look at the different 3 sine over square root of minus cosine square. So here's an 8 integral of 3 sine x over square root of 1 plus cosine square x dx. Now one thing, again, it looks not as quite the same. If you look at the strategy here, you have sine and cosine with power, this is what you do. Tangent and secant, this power is what you do. Sine mx and cosine x, okay, so that's number 7, that's what we use. Notice that 7 is not the same as number 1 type problem because the argument 5x and 3x are not the same. Okay, so you cannot use substitution. And likewise, number 8, if you look at the strategy here, well, it doesn't quite fit into any technical measure here for that one. So that's why I say we must keep in mind why it works and understand why it doesn't work, why we do substitutions or why we change the power. Now in this case, I still see sine, I still see cosine involved, so sine cosine together, that's nice. In fact, we can still use substitution, right? Because if I let u be what? Cosine x. Okay, u on cosine x. And why I choose that? Well, because the derivative cosine is negative sine of x dx. And I can't do it when you have you can do it when you have sine x dx there. Again, just off by the constant, and we can always do the same trick. And let's put out 3, and I have sine x. Let me remove it and put a sine x next to dx. So I have 1 over 1 minus cosine square x there. Okay, so you see that I need negative sign. So all I do is multiply it by negative 1 there, negative 1 there. Okay, that would allow us to change that to du, and that becomes a u. So our integral now is 3 times the integral of 1 over root of 1 minus u squared. Right, 1 forget the negative sign here. So now you have this integral. So do you remember how to integrate that one? Remember this is the arc sine. We done that in 8.1. So that turned out to be arc sine of okay, so we're going to do arc sine of u first because our variable is u is here. plus constant, but by substitute back, this integral becomes -3 arc sine of plus u again, and cosine x plus c. Okay. All right, so I guess that finished the number 8, which is the 8.3 trig integrals.